Hey guys, welcome back. Today we're going to talk about LeChatelier's principle. It's a fun name to say. Just basically looking at shifting equilibrium. So when a reaction is able to reach equilibrium, sometimes we want to actually move it in one direction or the other. And a great example is the Haber process, which is how we make ammonia, which is NH3. Um, NH3, if you don't know, is ammonia is really valuable in agriculture. It's a great way of getting nitrogen back into the soil, so it's a great fertilizer. It's used in large industrial cooling, like refrigeration, stuff like that. So there's a lot of uses for it. But if you want to produce it in as high a quantity as possible, you don't want to just put some nitrogen and hydrogen together in a tank and just kind of hope for the best. Um, or come back a couple minutes later and get your NH3, because within that within that reaction vessel, within that tank, you're going to have a lot of the reverse reaction happening. And so if you want to maximize the amount of NH3 that you're making, you have to utilize LeChatelier's principle. LeChatelier's principle says when a system at equilibrium is stressed, the system shifts in the direction that relieves the stress. By stress, we just mean change. So if we allow the system to reach equilibrium, let's say we give it a minute or two to react and it reaches equilibrium, um, we can do something to change the system. We can change the temperature. We can change the concentration of reactants or whatever product even, and that is considered a stress. It's a change in the equilibrium system, and that stress then is naturally counteracted by the system itself. So, um, for example, a possible stress is change in concentration. So if you wanted to produce as much NH3 as possible, what you would do is you're trying to favor the forward reaction. You're trying to get the forward reaction to happen um, faster or more so that you're producing more of the NH3 rather than the N2 and the H2, which you don't want. So how do you get the forward reaction to happen faster? A couple of ways. One would be to take out the NH3 that's forming. So if you take it out, if you have a process for removing the NH3 that's forming, the reaction will actually speed in the forward direction to make more. So if you take out the NH3, put it in a separate container, and you continue to do that, the reaction is going to continue to be favored in the forward direction to produce more because of what you've taken away. And at the same time, if you were to add more N2 and H2, which of course you're going to need to do because if you're taking away the product and the forward reaction is speeding up, eventually you're going to run out of N2 and H2. That's going to be another stress that's going to cause the reaction to go forward, because if you add more of something, the reaction is going to shift to use it up. Okay? So a change in concentration is one way that we can stress the system. Um, and if you kind of think of it as, in the Bozeman science guy used like a seesaw as a visual. So if you have reactants on one side and products on the other, if you increase the amount of products, then the seesaw is going to kind of tip down in that direction because it's going to be heavier on the side. The reaction would then naturally shift backwards to try to create more reactants to balance out that seesaw. So that's one way to think about how Le Chatelier's principle works. Just imagine that seesaw. If you put more of something on one side, the reaction is going to shift away to use it up, or you could say a way to balance out the seesaw by making more of the stuff on the other side. Okay, so another stress is change in temperature. Now, the change in temperature depends on us understanding how heat is involved in the reaction. So, for example, with this production of ammonia, it happens that we have like I think it's like 92 kilojoules or something like that on the right hand side. If I include the heat. So if it's endothermic, it's exothermic in the forward direction, it's endothermic in the reverse direction. So if I add heat, just think of that heat as being one of the products, just like ammonia. So adding something to the right-hand side, adding something to the products is going to make that seesaw tip down on that side. And the result of that is the reaction is going to try to make more or use up that heat and shift in the reverse direction. So if I want to if I want to produce more ammonia, and again I'm trying to shift this reaction in the forward direction, um, do you think I would add heat or remove heat? Yeah, I would probably want to remove heat and do this reaction at a colder temperature, because by doing this at a colder temperature, the reaction is going to try to generate more heat, and the direction that generates more heat is the forward direction. So by cooling this thing down, I'm always going to favor the direction that is exothermic. And in this case, that's the forward direction, which also produces more of the ammonia. So a couple of things we can do to produce more ammonia. One thing we've already said, take away some ammonia, which is going to make the reaction shift forward to produce more. Um, Add more nitrogen or hydrogen or both. That's going to cause the reaction to shift forward to use it up. Or we can take away some heat. We can lower the temperature. That's going to favor the exothermic reaction. That's going to give off more heat. Okay. Another example of that, and we usually do this one in class, but this reaction system is N2O4 gas plus heat gives NO2 gas. And this is actually the poisonous brown stuff in the balance I needed 2 there. This is actually the poisonous brown stuff that we made when we reacted the nitric acid with the copper penny on the very first day of school back in August. That was this stuff, the NO2. It's poisonous, and it's brown, smells a little bit like chlorine, nasty stuff. But if you do it inside of a sealed container, one of the cool things you can do is you can put, so the original color of the mixture, now first thing you have to understand, and this is where students have trouble sometimes, is that the N2O4 and the NO2 are both present because, oops, yeah, there we go. This is a reversible reaction. And so after just a few seconds, we're going to reach equilibrium. And if you look at this middle vial, that contains, actually all 3 of these vials contain both of these substances, N2O4 and NO2. So let's just focus on the middle vial for a second, though. So that was at room temperature. You've got a mixture of N2O4 and NO2 in there. And it happens that N2O4 is clear or colorless, and the NO2 is brown. Okay? And so it makes it for a very easy demonstration of the effect of temperature on this reaction system. Because if I take that vial and I put it in some hot water, you can see it's on a hot plate here, it gets a lot darker. Okay? Now, hopefully it makes sense why that would happen, because if we're heating up the reaction system, the direction that's going to be favored is always going to be the endothermic direction to absorb that heat. So which direction would this reaction go if we add heat, forward or reverse? So hopefully you said forward, because, well, for one thing, you can see on the hot plate it gets darker brown, right? Which coincides with making more of the product of the forward reaction, the NO2, which is brown. But also, if I add heat, the reaction is going to try to take it away. It's going to try to use it up. And the direction that uses up heat is the forward reaction in this case. It's the opposite of the previous reaction we just looked at. The endothermic reaction is the forward reaction. So adding heat is always going to speed up the endothermic direction in an equilibrium system. Cooling things down is always going to favor the reverse reaction, and that's what you can see here. You've got the other vial that has been put into some ice, and you can see it's gotten clearer than the original vial. And that's because the exothermic direction is now being favored. It's trying to give off or generate heat to make up for what's been taken away. Okay, then the last thing we can do here is change the pressure. Now this only works if we have gases in a different number of moles of gases on either side of the equation. So let me rewrite the equation we were just talking about here. So N2O4 I'm going to leave the heat out because that doesn't really have much to do with this particular example, but of course it would still be on the left-hand side of the equation. And these are both gases. And so what's happening here is on the left side, I have 1 mole of gas. Oops. And on the right side, I have 2. And so because I have a differing number of moles of gas on each side, when I add pressure, there will be an effect that is a stress. So here I have some of my N2O4 and NO2 in a syringe, okay? So like a piston. And what this allows me to do is here's my starting case here. And I counted them up. I think there's like 24 of the little red ones. And so the red ones represent the brown in the NO2, okay? So the reason that they show this picture and that you can count the little atoms or molecules is you can see how they change. What's happening here from the first syringe to the second one is they've just pushed the piston in and made the volume smaller, which of course is going to do what to the pressure, right? It's going to increase the pressure. Now the first thing you're going to notice is, well, wait a minute, it got darker, right? So if it got darker, is that because the forward reaction was favored because the NO2, which is on the right side, is brown, right? So if it got darker, it must have favored the forward direction. Well, actually, there's another reason that it got darker. It's not because it's favoring the forward direction. It's just because you're putting more of that brown gas in a smaller space, right? So you're increasing the concentration, all right? So there's no shift in equilibrium that has happened from point A to point B. And you can see that with the illustration by just counting up how many NO2s you have. You still have, I think it's 24, but it's somewhere around there. But they're the same from A to B. The only reason it's darker is because the concentration is increased because the volume is decreased. All right, now here's the interesting thing. Here's where LeChatelier's principle comes in. If you look at step C, you can see that it's gotten clearer even though the volume is still smaller. The volume is still smaller, but we now have fewer of the NO2s, which tells you the reverse direction must be favored. So the question is why? Okay, and you can count them up. I think there's like 17 or 18 of the little red guys instead of 24 or whatever there was in the previous one. Then that, again, is illustrating at least that the reverse direction would be favored. So why? And the answer is because by increasing the pressure, according to LeChatelier's principle, the system is going to try to decrease the pressure. Whatever the stress is, it will always try to undo it. So if the stress is that we've increased the pressure, the reaction system will always try to decrease the pressure. The only way that that can happen for the reaction system is if there is a direction, forward or reverse, that decreases the number of moles of gas. So you can see here we have 2 moles of gas on the right and just 1 on the left. So by shifting to the left, which is what's happened down here in this final picture, we actually have fewer molecules. And of course, by having fewer molecules in that given amount of space, we have less pressure, right? So shifting to the left for this particular reaction produces half as many molecules. So because on the right side we have twice as many moles, twice as many molecules. By shifting to the left, we're going to produce fewer molecules. And I misspoke a little bit. We don't have half as many molecules in picture C as we had in picture B, but we do have fewer because even though we're shifting to the left, we're not shifting completely to the left. We still have some of the forward reaction happening. So we're not actually cutting the reaction or the molecules in half by shifting to the left, but we are cutting it down a little bit, and we will have fewer molecules and we will have less pressure. Okay, let's move on to a couple of questions here for you guys to answer. Multiple choice. We'll pretend we're taking a test even though we're not. Which of the changes listed below would shift the following reaction to the right? So which one would shift it forward? Take a look at those and see what you get. Okay, so let's take a look here. Which of the changes listed below would shift the reaction to the right or shift it forward? Would adding more Cl2 do that? If I add more Cl2, what's the reaction going to try to do? Right, it's going to try to use it up, which means the reverse direction would be favored. So that's not a viable answer. Okay. What about the removal of oxygen? If I remove oxygen, the reaction is going to try to make more. It's going to do the opposite. It's going to try to relieve that stress. And making more means shifting to the left, right? So that's not a viable option. Take a look at C, increase in pressure. Okay, so we have to count moles of gas on both sides because if they're the same, or if there are no moles of gas on either side, um, then changing pressure is not going to do anything to the reaction system. It's not going to even be a stress. But it looks like I've got 5 moles of gas on the left and only 4 on the right. So if I increase pressure, the reaction system is going to try to make less gas, which in fact would shift it to the right, which is making 4 moles instead of 5. So it looks like the correct answer was in fact C. And of course D, we always want to check our other options, but if increase in pressure is correct, then decrease can't be correct. Okay, try another one. In a reaction at equilibrium that makes more moles of gas than it consumes, what is the effect of increasing pressure? Might be a good idea to make a hypothetical example. So, for example, you might say A, which is a gas, goes to, let's say, 2B, which is a gas, so it's making more than it consumes. What do you think there? Okay, if we increase the pressure, the reaction should shift to the direction that makes fewer moles of gas, right? So it should shift to the left, all right? So if it's shifting to the left, I'm going to go ahead and just do that. So if it's shifting to the left, the reaction makes more products? Nope. The reaction makes more reactants? Yep. The reaction is unchanged? Nope. The answer cannot be determined? Nope, it can, and it's B. All right. In an endothermic reaction at equilibrium, what is the effect of raising temperature? So again, you might want to draw this out. First of all, let me say, if it just says endothermic reaction, by default, it means the forward reaction is endothermic. Okay, so essentially we're saying A plus heat, and then there's B on the right side. So what do you think? Okay, so if we raise the temperature, we're adding more heat, right? So if we're adding more heat, the reaction is going to try to use that heat up. And so it's always going to, whenever we raise the temperature, it's always going to shift in the endothermic direction. So that means that way, forward. So that does mean the reaction is going to make more products. So just double check to make sure you haven't missed anything. Of course, if it's making more products, it can't be making more reactants. It can't be unchanged. And those are some kind of lame answer choices. Oh well, I probably didn't write that one. All right, if a reaction has an equilibrium constant just greater than 1, so this is not a LeChatelier's principle question, just just an equilibrium question. Go ahead and see if you can figure that one out. Okay, so it can't be irreversible because it wouldn't have a KEQ if it didn't reach equilibrium. Spontaneous doesn't really have anything to do with what we're talking about. All right, so it is reversible. It's got to be C or D. If the KEQ is greater than 1, and KEQ is products over reactants, and it's greater than 1, that means the products are greater, so favoring products. Not by a lot, apparently, because it says just greater than 1, but it does at least favor the products. Okay, a couple questions here we'll do these one at a time, based on this reaction system. So this is getting back to LeChatelier's principle. How would the reaction change, if at all, due to added pressure? Okay, so there are 3 moles of gas on the left and only 2 on the right. So if you added pressure, it's going to shift forward, and that is to make fewer moles of gas. All right, hopefully that makes sense. 3 on the left, 2 on the right. It's going to shift forward. What about the next question? How would the reaction change, if at all, due to the removal of oxygen, and why? Okay, hopefully you said reverse to make more oxygen, right? So the way I always look at this is, draw some arrows. If I take away oxygen, if I make it go down, the reaction is going to try to speed up in the direction, whichever direction makes more. So that would be reverse, right? All right, final question. How would the reaction change, if at all, if you were to lower the temperature, and why? Okay, if we lower the temperature, anytime we lower the temperature, the reaction is always going to speed up in the exothermic direction. In other words, whichever side produces heat, which would mean, in this case, forward, to make or release more heat. Okay, so again, it's kind of like, think of heat as a substance. And if we lower the temperature, it's like taking away heat. Well, which direction would make more? Forward, right? So if imagine that seesaw, if we lower the side that has heat on it, it's going to try to produce more, bringing that side back up into balance. All right, guys, that is all I have for you. I think a 22-minute video is probably plenty. You guys enjoy your weekend, and we will see you back next week talking about acids and bases.